Good afternoon, good evening, good morning, everyone. It's our great pleasure today to welcome Joel Wilner from Dartmouth College, who will talk about a big question, glacial versus fluvial erosion rates. Before I give Joel the floor, I also want to highlight that Tamara is helping me today sharing this Landscape Live talk. We're getting to the end of the season, as we just discussed before recording. We will have two more talks following this by Andrew Gunn and Ji Wei Xu. This talk will be uploaded to YouTube after the end of the recording, and you will find our long collection of talks there. Go there if you're online. You're already there if you're on YouTube. We have about more than 100 talks right now there. So today, Joel Wilner. Joel comes to us from Massachusetts. He, in 2018, finished his BA at Middlebury, followed up by a Master's of Science at Brown University, finishing in 2021. And this is when he joined Dartmouth College to start his PhD. And that's what we're going to see today, at least part of the last 4 years of work, I think, for Joel at Dartmouth. Joel, take it away.
All right. Thank you, Luca, for that introduction. And thank you for the invitation to speak here today at Landscapes Live. I'm very honored to be here. So as Luca mentioned, I'm a PhD candidate at Dartmouth in the US. And I'm going to talk to you today about this big question of the relative efficacy of glacial versus fluvial erosion rates around the world, and also contextualized a bit by limits to the timescale dependence of erosion rates. Okay, I want to gratefully acknowledge my collaborators on this project first. This was a group effort that stemmed out of a graduate seminar course at Dartmouth, actually. I really want to thank all my collaborators, especially the co-leads on the project, a fellow graduate student, Bailey Norden, and professors Brennan Keller and Marissa Palusis, who were completely instrumental to this work. All right, I want to start off today with this image I took of Russell Glacier in Western Greenland. It's this land-terminating outlet glacier near Kangerlussuaq in Greenland. And I think it's appropriate to show this image because it sort of sets the stage for a number of the different erosive and depositional components that will be relevant to today's talk. You have glacial till abutting the glacier margin, bedrock that the river is ostensibly incising into, fluvially transported sediments, gently sculpted glacier foreland, and glacially transported moraine sediments. It's these sort of glacially transported sediments that someone like Peter Martel in this 1744 letter to a friend of his after a trip to the Swiss Alps would have described as, quote, a kind of mound of great stones which the ice has raised. And all this to say that geologists have been noting sediment in a glacial transport and depositional context for quite some time now, for several centuries. And across these centuries, several key questions in the realm of glacial erosion have emerged. Most notably, how powerful is glacial erosion exactly? Right? We have this stark contrast between somewhere like Norway, where you have these dramatic fjords, versus somewhere like Western Greenland or the Canadian Shield, where you have this gently rolling paraglacial topography, or closer to my home in the Northeast US, you have somewhere like the Finger Lakes, which are these really dramatically over-deepened glacial lakes surrounded by gently rolling topography. So yeah, so are glaciers protective agents unable to erode even unconsolidated sediments, or are they the most dramatic erosive agent on Earth? And I think the question is summed up by this great quote from William White in this paper from 1972. It seems that ice sheets can be able or feckless erosive agents in the same place at different times, which I think is a great quote. So first, we need to understand how do glaciers erode. So this should be familiar to many people here, but it's just important uh, to set the stage here. Of course, we have abrasion of bedrock through glacially transported clasts at the bottom of a glacier. You have the idea of plucking or quarrying, where you have this pressure differential over a glacial rise that exploits pre-existing joints and cracks in the bedrock and actually plucks out debris from the lee side of that bedrock rise. And then more recently, a mechanism has been proposed called glacial ripping, where you get this sort of disintegration or lateral spreading and ripping of a glacial rise as a glacier you know flows over the rise. And this has been observed in many parts of the world, including Scandinavia. So you have these three mechanisms of glacial erosion, at least. How do we measure and quantify glacial erosion? There's a variety of mechanisms. There's cosmogenic methods, such as surface point measurements or detrital measurements that average over a basin. Thermochronometric measurements that rely on the thermal properties of minerals as they rise through the Earth's crust. Volumetric measurements, so this includes proglacial rivers and catching sediment that flows out from a glacier. And this is really robust to a number of scales. It's a very useful technique. And then relief measurements, which can be thought of as similar to volumetric measurements, but without that volumetric dimension to it. So we have these different measurement methodologies of glacial erosion, and this will come into play throughout this talk. So I want to motivate this talk with a couple of big outstanding questions in the field that are subject to great debate. So there's, of course, the question of Cenozoic cooling and glaciation. Did Cenozoic cooling and subsequent glaciation enhance global erosion rates? We see this drawdown in surface temperature over the course of the Cenozoic period, especially in the last 5 million years. That's coincident with a increase in sediment delivery to the world's oceans. So this has led many authors to say that there's some causal mechanism between climate and glacial erosion in this context. Then there's the question of the great unconformity, this mysterious unconformity that you need to account for 3 to 5 vertical kilometers of eroded material somehow. And some authors, including Brennan Keller, who is a lead author on this paper, have posited snowball Earth to be a cause of this unconformity. Both of these questions are subject to considerable debate ongoing in the literature. Now, complicating any thorough assessment of these questions is the concept of the Sadler effect, which you may be aware of, this apparent inverse relationship between erosion or deposition rate and measurement timescale. So you can see on the right this figure from that original Sadler paper in 1981, where you have the erosion or deposition rate on the y-axis and measurement time span on the x-axis. And you have this really distinct decrease in erosion rate as measurement timescale increases. So you get longer measurements yield slower apparent rates of erosion or deposition. And this is generally attributed to the presence of unobserved sedimentary hiatuses in the record, right? If you have a shorter measurement time span, you're going to miss some of those sedimentary hiatuses. And the practical effect of this is that it can mask true erosive changes in the record, and it can complicate a thorough comparison of fluvial erosion rates versus glacial erosion rates if you have this Sadler effect acting in different ways upon the sedimentary record. So we have this really two-pronged objective in this work here. We want to really quantify the relative efficacy of glacial versus fluvial erosion at a truly global scale, while also understanding the timescale dependence of erosion rates. And in doing so, we create this new global compilation of glacial erosion rates and associated metadata, such as measurement methodology, basin area that you're measuring over, measurement time span. Um, yeah, so in this graduate seminar course, through the combined strength of 7 graduate students, 1 undergrad, um, 1 postdoc, and 2 faculty mentors, we scoured the literature manually for as many glacial erosion rates as we could find and compiled those rates as well as associated variables that may be of interest. And we came up with something that looks like this. This is just one small snippet of the compilation. If you're interested in seeing the full compilation, it's available online in the GitHub repository. Yeah, so this new global compilation of glacial erosion rates includes 427 glacial erosion rates, which is approximately, well, it's an order of magnitude greater than the next largest previous glacial erosion rate compilation. And it truly spans the globe in a variety of glacial settings that we've here categorized as alpine, alpine tidewater, non-continental, high latitude, continental, and ice stream. And we contrast these glacial settings and glacial erosion rates with previously published compilations of non-glacial, mostly fluvial erosion rates, many from the Octopus compilation. And these are denoted in gray. So taking a first look at the data, we see that different glacial settings exhibit different characteristic mean erosion rates. So with alpine tidewater and alpine glaciers being the fastest, with continental glaciers being among the slowest, which makes sense. But we don't see that clear negative correlation between glacial erosion rates and measurement timescale that we might expect in a Sadlerian context. We do see it in the background for those non-glacial erosion rates. So that's interesting, why we would see it for the non-glacial rates, but not clearly for the glacial rates. So next we took these data and plotted histograms in log mean space. And we came up with this histogram comparison where you have erosion rate on the y-axis and number of measurements on the x-axis. And we see that there's a characteristic log mean glacial erosion rate that's an order of magnitude greater than that of fluvial erosion, 0.51 millimeters per year versus 0.067 millimeters per year for fluvial erosion. And this has some potentially large implications that I'll get to later in the talk. But first, I want to ask the question, is this difference real? Or is this a product of certain biases that exist in the sample space of glacial erosion rates versus fluvial erosion rates? Yeah, so we plotted erosion rate versus a number of potentially relevant independent variables. So first looked at precipitation regime taken from CHELSA reanalysis climatology data, and plotted glacial rates versus non-glacial rates against precipitation, and find that, okay, for glacial erosion rates, we do see this higher characteristic erosion rate for glacial settings compared to non-glacial settings, especially at higher precipitation values. Next, we looked at regional average hill slope. So looking at erosion rate versus regional average hill slope for glacial versus non-glacial rates. Again, we see this higher characteristic glacial rate across hill slopes. And note that there's this lower slope for erosion rate versus hill slope for glacial settings versus non-glacial settings, which is to be expected since glaciers are more dependent on surface slope than bed slope. but this will come into play later as well. Then we looked at erosion rate versus absolute latitude. Again, glacial rates are more efficient than non-glacial rates here. And finally, erosion rate versus basin area that you're measuring over. Same thing, glacial rates more efficient than non-glacial rates. So we have all these independent variables that we've plotted against. We also have lithology, which you may be wondering about. So we plotted against crude categorizations of lithology from macrostrat data and found that on average, glacial erosion outpaces fluvial erosion across these different lithologies. Note that glacial erosion rates are fairly agnostic to the type of metamorphic igneous or sedimentary rock that is in the substrate. So this difference appears to be real in that it's robust to many relevant variables. Yeah, so we can make this claim here that glacial erosion on average far outpaces fluvial erosion by an order of magnitude. But what about this timescale dependence that I keep referring to? This was important to quantify. So first, we looked at glacial erosion rate versus timescale for different basin sizes and plotted it in the color here by measurement methodology. Right. So for these smallest basin areas, less than 0.1 kilometer squared that you're drawing from, these are mostly cosmogenic samples, although not all. But you do see this Sadlerian timescale dependence emerge. You do see it that the slope, this timescale dependence with erosion rate for these smallest basin areas. However, as we increase the basin size for glacial samples, this timescale dependence disappears. So we only see this timescale dependence in glacial samples robustly for the smallest basin areas, which correspond to mainly cosmogenic measurements. Then we have this comparison in the same space, but with fluvial erosion rates, where we do see this really distinct timescale dependence emerge, regardless of basin area. And it's most notable for cosmogenic measurements as well. So plotting glacial, fluvial, and subaerial erosion rates versus timescale for cosmogenic methods on the top versus all other methods in the bottom, we see this really clear distinction begin to emerge between Sadlerian cosmogenic effects versus erosion timescale space that is non-Sadlerian. So it's also important to note that this slope of this Sadlerian trend corresponds to a length scale of 600 millimeters. If you take the units on the y-axis and the x-axis, it corresponds to a length scale, which just so happens to be the average penetration depth of cosmic rays into rocks, below which you get efficient attenuation of cosmic rays. So we deem this to be a measurement thickness bias that manifests most notably for cosmogenic samples. So this particular flavor of the Sadler effect is a measurement thickness bias, we presume. Now note that it's that this volumetric average and the cosmogenic average here in this fluvial setting, they're quite similar despite cosmogenic rates having this timescale dependence. So we think it's possible, in a sense, to see past measurement thickness biases by comparing these log mean erosion rates between different methodologies. So that may be one way around the Sadler effect. So those were data analysis results. I want to go through these numerical experiments that we ran to supplement this big data analysis. So these numerical experiments are inspired by the work of Ganti and others. And first, I'm going to walk you through this fairly complicated plot showing regular events. So if you look at this example time series here, you have a, a simulation suite of regular erosive or depositional events. So I'll talk you through some of the specifications of this. So we simulate regular events, regular erosive or depositional events at a frequency of one event per year with a mean absolute value pulse of 1 millimeter of displacement. So we make this distinction between unidirectional processes and bidirectional processes. So this is an important distinction. You can think of unidirectional processes as being, those processes that are erosive in nature that can't, in a sense, redeposit their sediments, their erosive products upstream. And this is relevant to glaciers. You can't, for example, redeposit a glacial sediment back up underneath the glacier. Whereas bidirectional processes are those sorts of processes that involve sediment reworking and can, in effect, redeposit their sediments upstream. And here we're talking mainly about environments that are below base level, such as tidal or deltaic environments, that exhibit this sediment reworking, and they're truly depositional environments. So for these unidirectional processes, we draw from an all positive half normal distribution. Whereas for bidirectional processes, we draw from an equally positive and negative symmetrical normal distribution. And for both of these, we run for 100,000 iterations. So I'll walk you through what we're seeing here exactly. For regular events, we see that these unidirectional processes have this constant mean rate across timescales of 1 millimeter per year. And that's unsurprising because you're increasing total displacement linearly with time. So average rate remains constant. Versus for bidirectional processes, you have this timescale dependence, this diagonal line, the Sadlerian slope that arises. And it's akin to Brownian random walk motion, which has this well-recognized scaling with the square root of time, t to the negative 0.5, where that negative 0.5 manifests as the Sadlerian slope. And this is, characteristic of a Brownian particle that may be appropriate for a tidal or deltaic environment below base level. So we see that for regular events, these geologic rates may be inherently timescale dependent only for bidirectional processes. And we deem this particular flavor of the Sadler effect to be an erosion redeposition bias. So now here's a more complicated plot still that shows a rare event framework. So we have this regular event framework and we contrast it with a rare event framework. Note the differences between the example time series here and the irregular example time series here. Also note this averaging timescale panel on the bottom here, where it shows the proportion of events in a given interval in the rare event framework. So for short averaging timescales, understandably, you have many timescales where you don't have an event in an interval or have very few events in an interval. Whereas if you increase the timescale, you get more eventful. You get more events in the interval. And then, until you reach a maximum hiatus duration, and then it's akin to the regular event framework here. So I'm just going to talk you through the irregular event simulation specifications. So this frequency is drawn from a truncated Pareto distribution, long-tailed distribution after Ganti. For numerical reasons, we increase the mean pulse amplitude to 10 millimeters rather than 1 millimeter. We run, again, over 100,000 iterations using the same distinction between bidirectional and unidirectional processes. And we start the averaging timescale at a random point in order to avoid starting each interval with an observation, which would introduce some sort of bias. So I'll walk you through this plot step by step because it's fairly complicated. So you have this unidirectional framework where you have all intervals considered, eventful and uneventful, which I've highlighted here. So again, this has this lack of a timescale dependence, a slope of 0. And again, this reflects steady or one-way accumulation, so erosion only. So again, coming back to my example of glacial erosion where you can't redeposit upstream. When you're considering, again, unidirectional processes, but only eventful intervals, this slope before the maximum hiatus duration shifts to approximately -0.5, that magic number, that Brownian number. And it mimics the behavior of bidirectional systems in the regular case. So this is another manifestation, we think, of the this is a manifestation of the non-observation bias, which I haven't introduced yet, that arises when zero rate intervals are not observed. So now looking at bidirectional processes, you have the consideration of all intervals, both eventful and uneventful, where you have this slope of -0.5 once your time scale is greater than the maximum hiatus duration. And again, this is reflective of that random walk behavior. However, what's interesting is that shorter time scales, the slope, you still have a slope, a Sadlerian effect, but it's less than that -0.5 value due to the sparseness of events and limited signal buildup. And now perhaps most interesting is the bidirectional eventful intervals only consideration, where you have a slope that's actually steeper than -0.5 before the maximum hiatus duration is reached. And you get this, what we think is some sort of stacking of two different biases. You have a stacking of that non-observation bias that I introduced for the unidirectional eventful case, and that erosion redeposition bias that we're now familiar with. So you have these two stacked Sadlerian effects that occur for bidirectional eventful intervals. So put it another way, when only eventful intervals are considered, you get unidirectional processes that show timescale dependence, and bidirectional processes show a timescale dependence that's even steeper. Whereas when you include all intervals, not just eventful intervals, but eventful and these uneventful intervals here, the unidirectional processes show no timescale dependence, and you get this bias from excluding zero change intervals that we've here termed the non-observation bias. So that was a lot, but it all comes back to this ternary Sadler effect. So in summary, a Sadlerian timescale dependence on erosion rate may emerge if there exists at least one of a measurement thickness bias, so namely cosmogenic, an erosion redeposition bias, and or a non-observation bias. So we've here contextualized the Sadler effect in a few different ways. So now that we have these variables that we've compared our erosion rates against and we've contextualized it by the Sadler effect, we can get into these broader implications. So recall that we have this characteristic log mean erosion rate of glaciers that's an order of magnitude greater than that of fluvial erosion. And this has a first order implication that it implies that Cenozoic cooling and glaciation very well could have enhanced baseline global erosion rates. If you have cooling and you necessarily have glaciation, and here we've shown that glaciers are more efficient erosive agents than rivers, then you would expect to have more erosive products that make their way into the ocean. Secondly, getting to the other big question, note that the continental ice sheet erosion rates that we've quantified here, not even the fastest glacial erosion rates, but the continental erosion rates, so 0.26 millimeters per year on average. If you do the math, it's sufficient to produce the 3 to 5 kilometers of great unconformity material, which would be consistent with some previous authors who have posited that that snowball Earth glaciation could be a cause of such a large unconformity through erosive mechanisms. But getting to this point again, it's important to note that fluvial erosion rates, so those smaller erosion rates, could suffice too over albeit a somewhat longer averaging interval. So why favor glaciers for unconformity development? Well, if we come back to this plot of erosion rate versus regional average hill slope, recall that glaciers are less sensitive than rivers to regional average hill slope. Glaciers erode more efficiently than rivers at low hill slopes. So see this glacial line here versus this non-glacial, mostly fluvial line here. Rivers are perhaps more efficient erosive agents at these very high regional average hill slopes that you're getting at the angle proposed there. You're talking about landslides there. But at these smaller hill slopes, glaciers tend to be more efficient erosive agents. So if you get this large-scale glaciation and sea level drawdown, therefore you're going to spatially expand the erosive reach of glaciers to these low slopes upon decreasing the global base level. So global base level, in essence, and associated glacial erosion may perhaps be the limiting factor in unconformity development rather than the absolute value of glacial erosion rate versus fluvial erosion rate. So yeah, so recall this increase in sediment flux with late Cenozoic cooling. I'm going to talk about a geochemical argument here. And I'm not a geochemist, but this is just something that we all in this paper came up with to try to explain some of the phenomena that we see in some isotope, beryllium isotope trends in the marine record. So yeah, recall that we have this increase in sediment flux with late Cenozoic cooling. This has sparked so much debate in the literature with regard to a glacial origin or not. So here's a figure from Willenbring and von Blankenberg that suggests that stable beryllium-10 to beryllium-9 ratios imply long-term stability of global erosion rates during the late Cenozoic. You have these stable ratios implying stable erosion rates in both the Pacific and Atlantic. So we try to reconcile this observation with some of the observations that we've made up to this point in the talk with a sort of geochemical argument that why these ratios of beryllium might actually be underestimating the actual amount of glacial erosion that we're experiencing. So we have this plot here of concentration of beryllium versus pH in terrestrial surface waters. And note that you get this maximum amount of beryllium that can remain dissolved before precipitating out solution according to the saturation level. So higher pH levels significantly reduce the solubility of beryllium, and that impacts its mobility in water. You have higher pHs in these marine environments. You have a modern seawater beryllium concentration here, and then you contrast the marine system's pH with the pH of terrestrial systems, and you get this decrease once you reach a saturation curve line, and yeah, that's implying a number of things. our argument here, our chemical argument, is that glacial erosion produces like finely ground but relatively unweathered material in this cold environment. As this glacially produced but somewhat unweathered material enters the ocean, it encounters pH conditions that are significantly higher than it had on land, and you encounter this saturation curve. So subsequent chemical weathering at oceanic pH, as you increase the pH levels, that can limit the mobility of beryllium-9. So you get this large volume of glacially eroded but chemically immobile beryllium that simply isn't making it into the dissolved inventory in the ocean in a way that's reflective of the total glacial erosion rate. So you might get this stable oceanic isotopic ratio despite having potentially higher glacial erosion rates that we've argued for so far in this talk. Yeah, so that's our sort of hand-wavy geochemical argument that hopefully shed some light on some of the previously proposed implications of glacial erosion rates being more efficient than rivers and enhanced during the Cenozoic. So I'm going to conclude there. I'm going to leave you with some conclusions. We have this figure here that shows that on average, glacial erosion outpaces fluvial erosion by an order of magnitude, by 0.51 millimeters per year for glacial rates versus 0.067 for fluvial erosion rates. And this is robust to a number of variables that could theoretically play a role in creating a higher glacial versus fluvial erosion rate here. These results are at face value consistent with enhanced cooling-induced Cenozoic erosion and subsequent glaciation and glacial erosion. We've shown through data analysis and some supplementary numerical experiments that the Sadler effect is comprised of a few distinct biases that pertain to measurement thickness, most notably of cosmogenic measurements, erosion redeposition, and non-observation of zero rate intervals that could explain some of that Sadlerian effects that we're seeing for in the fluvial space. And then we have this erosion by ice sheets, by continental ice sheets, is sufficient to produce the degree of vertical erosion that's associated with an unconformity, such as the Great Unconformity during snowball Earth glaciation. Although we make the argument that sea level drawdown and decrease in base level may be a critical consideration. And if you want, you can scan this QR code that would lead you to our paper that was published late last year in Science Advances on this work. And I'm just going to throw out there that I'm currently seeking a postdoctoral position in glacial erosion or a related field, so it'd be great to get in touch. And yeah, I'll leave you with these conclusions and would be happy to answer some questions from the chat. Thank you.
Thank you very much, Joel. This was really interesting. A lot to process. I'm still digesting part of the talk here, and I'm sure that there will be quite a few questions. People might be writing right now. I may want to start asking you, and yeah, drink some water if you need it before continuing. I think it was around slide, I think 38, and I noticed that you have this really enlightening presentation of the different rates as a function of the methods.
Mm-hmm.
And before asking a question about it, about what we see in terms of the trends, could you just remind us again, in light of that, how a volumetric rate of erosion is measured?
Yeah, so it's a quite a robust methodology that spans a few different sub measurements types, but you can think of it as averaging over a basin. So if you have a proglacial river, for example, that's outputting a bunch of sediment from a glacier, and you have, for example, a stream gauge, and you're measuring the amount of glacial sediment that's produced into that gauge, you're going to effectively produce a volumetric measurement that can measure over the upstream basin. And this could be, I say it's robust because it can be very small scale. So it can account for, say you have a few grains of sediment. You're gonna, in theory, measure that versus a huge influx of sediment into your river. It can measure that, it can quantify that as well, versus some of these other measurement methodologies are limited by certain characteristics and can't
All right,
achieve
great.
that.
Yeah. So it's also through the measurement of a flux over a period of time, you get back to your volume. It's
Yeah.
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 Okay. And so then my follow-up question for that is, so we have here this visible Sadler effect in both the small scale catchment and the method of the cosmogenic method.
Mhm.
Um, the and I think that you cover actually part of that answer, but it would be good to hear it again. The fact that we do not have we do not see a Sadler type effect in larger catchments. Is it inherently from the larger size that averages more processes and more events in this larger basin, or is it more inherent to the method alone?
That's a good question. I think it's more inherent to the method alone, um, in that the method, in the case of glacial samples at least, is cosmogenic methods are restricted to largely point measurements. Here we call it cosmogenic surface measurements. So that's going to lead to this distinction that we see between the left panel and the right two panels. So yeah, I would say it's more measurement limited than inherently basin scale limited, if that makes sense.
All right. Thank you. Tamara, you want to take it from
Yeah.
here?
Yeah, Joe, we have some questions in the chat, so I'm gonna read it. We have Colleen asking, thank you for your presentation, Joe, super interesting. I might have missed it, but have you extrapolated your results at the global scale? That's the first question. And then they say, because glaciers might induce more erosion at the local scale, but there are limited numbers of them, whereas rivers are virtually more numerous. So what is the global budget of glacial versus fluvial erosion?
Okay. So the global glacial budget of glacial versus fluvial erosion. Yeah, we don't really uh, talk about the precise budget of or volume of glaciers versus rivers that may act on a global scale. But if we come back to the map, come back a few slides. So, oops. Yeah, so we have our map here. It's true that rivers are more ubiquitous than glaciers for sure, and we haven't explicitly accounted for that in the quantification, but I suppose we did what we could in terms of the distribution of glaciers. We have Antarctic glaciers. We have a handful of tropical glaciers. But yeah, we don't account for that in a quantitative way in terms of biasing where glaciers might be, with the exception of this latitudinal erosion rate versus latitude that may be part of the answer to the question. Where glacial erosion rates, where available, are higher than non-glacial erosion rates at a given latitude on average. So I think that would probably be the best stab at answering that question. Yeah.
Right, thanks. And Colleen, thanks you for that answer. I'll move to a question by Emma. Thank you for the great talk first. Can you, and I think that's a question that I would have as well, can you explain a bit more the sample thickness bias for cosmogenic rates? I think there was a lot of information, it's super interesting, but could you go over that again?
Sorry, could you repeat that real quickly? The sample thickness?
Yeah,
Oh,
can you explain a bit more the sample thickness bias for cosmogenic rates?
Yes. So you have this 600 millimeter average penetration depth of cosmic rays into rocks, below which you get this efficient attenuation of cosmic rays. And I guess the question is probably getting at like a mechanistic understanding of why this might manifest as a bias. So yeah, it's a bit unclear, but I guess it makes sense in the sense that you plot this in Sadlerian space, you get this this distinct slope that happens to be the penetration depth of cosmic rays into rocks. So I think just at face value, we deem it a measurement thickness bias without getting too much into the distinct mechanisms underlying it. I think that would probably be my best stab at that question, unless you want to follow up.
So this would be this 600 millimeter. I'll let maybe Emma, give Emma a bit more time if she wants to elaborate further on the question, but this would be something that is for those basin-wide averaged rates?
Yes.
Right.
Yes.
And that's where, and that would be then linked to would you expect that 600 millimeter to be, and maybe here I'm missing some of my basics in cosmogenic, but would that change with the target of the measurement, whether it would be chlorine versus beryllium, or would this be inherently 600 millimeter across all of the systems?
Yeah, I think it's robust across many systems. So this the reason this fluvial slope for cosmogenics is so good, so distinct and straight there, is that the octopus data set that we derived a lot of these cosmogenic measurements from, it's very self-consistent. It uses a lot of the same assumptions, but I believe it does use different cosmogenic systems. So yeah, I believe it's robust to a number of cosmogenic systems, and even for the larger basin areas for these cosmogenic detrital systems. So not even considering these point measurements. So if you look closely here, you do even see a Sadlerian effect that begins to emerge for those largest cosmogenic detrital samples in the glacial regime.
Interesting.
I
Just
have a question.
go ahead,
Oh,
Tamara.
sorry. Look. Yeah,
Go ahead.
no, this is a question I was thinking because maybe I didn't fully understand. I don't think I fully understand the modeling and what bidirectional was accounting for versus a unidirectional. But my question is related to for example, when you measure an erosion rate from cosmogenic or any method that might be representing combined erosion by fluvial and glacial deposit, like the two processes, you might be getting a rate that is the result of both processes because a ton of catchments have rivers and glaciers. So I was trying to understand if that combined effort on erosion is represented by the unidirectional, bidirectional, but those might not be represented, but I just wanted to understand this too. And if they are not represented by these two unidirectional, bidirectional, how can we see that signal when maybe we're seeing a really high erosion rate because it's actually both?
Mm.
Yeah.
Yeah, so that's a great question. I think we're limited in the context of this data analysis framework and this compilation framework by what we could find in the literature. The literature sources tend to attribute the erosion to one or the other.
Mhm.
But you bring up a great point that in actuality, you very well may have a combination. Um, so this numerical experiment doesn't explicitly take into account any sort of combination of fluvial or of fluvial and glacial combined erosion. Although I suppose in the bidirectional case, um, since it's equally positive and negative, this distribution, you could, in theory, have a sample that lies somewhere along that distribution that has experienced both. So I
Mhm.
think, yeah, I think if you combine them, then it would tend to lie in that bidirectional space. Um, rather certainly not the unidirectional space if you're considering
Right.
the fluvial component. So yeah, thanks for bringing that up.
Yeah.
I would actually have another question on I think it would be the next slide, or the ones where you compare, um, maybe it's a few slides later. Yeah, with the once you have the rare events. But before I ask my question, just to convey the good words, thanks for a great talk from Susan and Bob Anderson that have to leave right now because it's a packed day today for them.
Hmm.
Just so you know. Um, the first clarification question, and then I'll ask the main one. When you say eventful, it means it contains at least one event. It doesn't mean it's full of events.
Yes, exactly.
Okay.
That's
So,
exactly right.
and now this is really cool to present it like this. It's a lot of information. I was wondering if, so here we have just unique events that happen rarely. Um,
Mm.
if this comes on top of a continuous rate of erosion, I'm maybe thinking this way of, let's think of abrasion,
Mm.
that this grinding that happens all the time, and then we have some plucking or this ripping that you talked about at the beginning. Is this shifting somehow the hiatus duration? Does that change anything in that behavior, or not?
Mm. Yeah, I suppose if you went from an abrasive regime to a more irregular plucking regime, um, yeah, I suppose you would transition from a regular to an irregular time series. Um,
Yeah. So
yeah, I
yeah,
think,
just having this addition of punctual events on top of a baseline, would it, in this phase space that you show here, would we just simply shift all of the points up
ah,
by having the baseline erosion that's happening all the time? Or would that also change somewhat uh, the slopes or the behavior of the system? I have a difficult time to understand. I think it would just shift everything up, but I'm not sure.
yeah, to be honest, I haven't thought about it in that way. I would have to think about it some more. Would it shift it up? Um, I don't have a good answer for that
Okay.
right. I'll have to think about that some more. And
Yeah. It's really cool. It's really cool to see it plotted like that.
Yeah. So we have another question in the chat. Kai says, thanks for the great talk. How is the cosmogenic detrital method used to faithfully quantify erosion rates in glacial basins? And then how is cosmogenic nuclear production rate determined for parts of the basin covered and eroded by ice?
okay, so the second question first. the cosmogenic production rates. I'd have to. Of course, production rates are latitude, elevation dependent. So I guess the question is getting at discrepancies in the production rates for large basins. Yeah. So every paper that presents a cosmogenic rate is different in that way, but I assume that they would average some production rate at the sample location in most cases, rather than take it from the sample location rather than the basin as a whole, although I may be wrong there. And what was the first question?
The first question is how the cosmogenic detrital method used to faithfully quantify erosion rates in glacial basins.
Okay. Yeah, so cosmogenic detrital, versus point measurements, right? Yeah, so
yeah.
Okay. I'm not sure I'm not sure if I have an eloquent answer for that. But again, I think it comes back to the methodology of a given paper that implements a detrital measurement. There's going to be differences between different sources. And I can't I don't think I can say a blanket statement over if one paper that we've included here is, I guess, more faithful in the detrital sense versus another. But sorry, that's not a very satisfying answer. But I would, I guess, defer to the different sources that we've included here.
So amongst all of the data, which is this huge compilation you have created, you have this range of methods. Some, I suppose, are like very repeat, like the same repeated by the same group, but in different basins, different glaciers. But then you had at some point to make this, maybe you can go back to I think there's a plot where you color code by detrital versus, exactly. So here we see that, just to maybe contextualize again, the question of Kai, if I understand what the main point was, is most of the points that you have are those labeled cosmogenic surface, right? And then you have these orange points that are the cosmogenic detrital.
Mm-hmm.
So the cosmogenic surface are these point measurements?
Yes.
Okay.
Cosmogenic surface are the point measurements, and
Related
detrital.
surfaces. Okay, and detrital are the catchment wide.
And the catchment.
Yeah, exactly. Yeah.
Right. And then of course, then there's this pretty big variability in the ways these different methods were employed by the different groups.
Mm-hmm.
Okay.
Yeah.
I mean, I think this is almost impossible to have a clear, simple, eloquent answer for that. In that there's so much work from different groups that come into these rates here. So maybe if I can just ask you to go back to your conclusion slide as we wrap up, because we're hitting the hour, but we'll have that on the screen as we finish. This is a huge amount of work, and it shows some really nice observation, I think, that really contribute to answering a big question that many people have been wrestling with. Thank you again, Joel, for this talk. Everyone, have a look at the article. It will contain quite a few of the answers we were seeking here. If you're looking for a postdoctoral fellow to do some glacial erosion, you know who to ask. So before we leave, just to remind you that we are reaching the end of this season of Landscapes Live. We have 2 more talks before we end. Andrew Gunn is going to talk next week about Erosion landscapes, and Jiwei Xu is going to talk about, I don't know what exactly. We are still waiting for a title, but it's going to come very soon. Thanks, Joel. Thank you, everyone, for tuning in. Thank you for watching this on YouTube. And we'll see you next week. Bye-bye.